Hello, my name is Evan Ariel, and this is my Physics 2211 Lab 3 presentation. The purpose of this lab was to find the mass of a black hole based on the motion of an orbiting star and to calculate the initial velocity a ship would need to escape a black hole system when launching from an orbiting planet. The physical principles used in this lab were Newton's law of universal gravitation, the momentum principle, the parallel and perpendicular force components, and the velocity and position update formulas. We used two models in this experiment, a GlowScript program. The first one was a GlowScript program simulating the star's orbit, and a second GlowScript program simulating a spaceship launching from a planet orbiting the same black hole. Quick preview of our results. The average mass of the black hole was calculated to be 6.63 times 10 to the 33rd kilogram, and the initial velocity of the ship was negative 3.19 times 10 to the 7th by 1.48 times 10 to the 6th meters per second. We used Newton's second law to relate an object's change in momentum to the net force acting on the object. The equation was used because the star was undergoing forces. Finding the net force on the object, we could calculate the total change in velocity of the star and iterate to track its motion, and the planet's motion as well. We used Newton's law of universal gravitation to relate the force of gravity to the two masses of our source and our system and the separation between them. We also rearrange this formula to solve for the mass of the black hole. We use the velocity update formula to let us iterate our planet and star's motion so that we could calculate their orbits. The position update formula was used to use our new velocity to update our position in our orbits. In the experiment, in the part 1, the system was the star and the surroundings were the black hole, which was the source of the gravity. In part 2, the system was the spaceship and the surroundings were the planet and the black hole. For our initial conditions, in part 1, the mass of the star was 2 times 10 to the 30 kilogram. The initial time was 0 seconds. Our time interval was 1 day, and we used the Newton's universal gravitation constant. For part 2, the mass of the black hole was calculated to be 6.63 times 10 to the 33rd kilogram. The mass of the planet was 9 times 10 to the 20th kilogram. The mass of the ship was 7 times 10 to the kilogram. And the time interval was 1 second. We started at time equals 0 seconds, and we used Newton's universal gravitation constant. For some assumptions in this experiment, we assumed that the magnitude of the net force is equal to the magnitude of the gravity force. Because this force is not constant, we will assume that average velocity is equal to final velocity. And we can assume that the only force acting on the star and the ship on the star is the black hole, because it's in space, and the only forces acting on the ship are the black hole and the planet, also because they are in space. So this is the first GlowScript program, the black hole and the star. And up here, we are calculating momentum. And then down here, we're calculating the parallel and perpendicular components of the net force. And then here we use the universal gravitation formula to calculate the mass of the black hole and store it in a list. And then down here, we take the average of that list to get our result. This is the second GlowScript program. Up here, we're calculating the force of gravity on the planet. And in the second chunk of code here, we're calculating the gravity on the spaceship. And then down here in this third chunk, we are iterating the motion. So our results in the first part of the lab, our black hole mass was found to be 6.63 times 10 to the 33rd kilogram. And in the second part, the velocity was negative 3.19 times 10 to the 7th by 1.48 times 10 to the 6th meters per second. With this velocity, the ship can just barely escape the black hole. As you can see here by this pink line, it's very close to that black hole. This was about the absolute minimum that I could find by my guess and check method. Some sources of error is that we didn't use the exact value of g, and that this is a simulation, not an actual reality. For part 2, we used the guess and check method, so there's probably a velocity that has a few more decimal points that would be a bit smaller than the one I found. So what do the parallel and perpendicular components and the net force components, what does that all mean? So the parallel and perpendicular components of the net force and momentum are mathematically equivalent but represent different things. The components of the net force represent the directions of all the forces acting on the system, while the components of momentum represent the change in the system's speed and direction respectively. So what if you wanted to orbit the black hole instead of escaping the system? Well, your spaceship would need an initial velocity of negative 1.5 times 10 to the 6 by 7 times 10 to the 6 meters per second. This is because it would need to move faster in the y direction to match the planet's speed and escape its gravity, but also slower in the x direction so it can still be captured by the gravity of the black hole. Thank you for watching. Have a wonderful day.